Hi, I'm Mike Dopsa from Array of Stars, and today I'm going to break down some of the 6D research we've done with the Intel RealSense D400 series cameras. 6D refers to 3D objects and images that are represented spatially and can be navigated through with a 6 degrees of freedom camera. This differs from traditional 3D like stereoscopic images as it's truly spatial and not limited to a single viewing area. Semiotically, this also works as a logical successor to 3D and differentiates it from the traditional stereoscopic or 3 degrees of freedom content that people are already familiar with. Please keep in mind that each of these 4 examples are early research prototypes and are not representative of what could eventually make its way into one of our projects. To generate a complete hologram, you have to capture an image that is occlusion-free, which essentially means that there is no part of the object that's left uncaptured. You can think of depth cameras like a light bulb that would cast shadows on any part of an object or environment that light can't reach. Occlusion is exactly the same, as depth cameras capture no information where there otherwise would be shadows. This is a relatively simple problem. As any grip or photographer knows, the cure for an unwanted shadow is an extra light pointed in the right location. In this example, 4 RealSense cameras surround the subject in an outside-in facing array at varying heights and distances. Since the point cloud coming from the RealSense cameras is spatially accurate, the camera positions are matched in the real and virtual environments, generating a 6D hologram with no occlusion that does not need to be processed or manually aligned. This differentiates it from the workflow of DepthKit, AI-style studios, or other systems stereo-matching monoscopic cameras. As you can see, we're running this in real time without the expensive and time-consuming burden of post-processing. The camera streams here are raw. There's no post-processing or noise reduction of any kind, and the points themselves are a little too small for this resolution density. Both of these issues currently have solutions in the updated RealSense 2.0 SDK. So this existing workflow will dramatically improve alongside the natural progression of the hardware and software. I'm kind of pointing forwards, and you can see I'm looking in this direction, but there's no camera there. Just there, and there, and there, and there. There's also no camera above me. That doesn't stop me from doing something like this. So that's why it's kind of cool. This example for static capture works very similar to existing photogrammetry techniques, as multiple point clouds are generated, cleaned, and then combined into a single refined set. Shown here in that same array, you can simultaneously capture views with multiple depth cameras, or you can move through a space and capture multiple clouds from different perspectives. The latter cannot capture moving subjects, but is a great way to generate very high resolution images on a financial or computational budget. Once generated, you can combine 360 images and the completed hologram for advanced navigational flexibility in a single 6D scene. In many circumstances, it may be impossible or impractical to capture entirely occlusion-free content due to spatial or component limitations. In this example, we use an accurate 1-to-1 3D model of the environment as a background and project point clouds from the real world onto it. Because the RealSense camera's output is so accurate, a correctly placed point cloud lines up identically with the virtual model. This is analogous to matte painting in the world of film or VFX, as the unseen areas have an approximate placeholder, creating a more complete feeling image. Today's example is using simple primitives and materials, but a high-resolution photogrammetry-based model could provide an indistinguishable, or in fact superior quality backdrop to the capture itself. Instead of measuring and placing a depth camera, a spatially tracked camera can dynamically move through a space, adjusting its position and rotation every frame. This creates a volumetric flashlight, layering the real-world elements on top of the static model in whichever location the camera is pointing. Let's imagine this dynamic tracked camera is a mobile phone with a depth camera placed on the back. Now imagine 10 phones capturing in the same room. Multiple people will simultaneously combine projections to fill a space with more areas detailed than any single camera could provide. Pair this with SLAM and other computer vision techniques, and each frame can be stored, then refined through multiple passes to rapidly create an extremely high-resolution background model that continues to improve over time. Considering the Face ID cameras on the front of the iPhone X series devices already have depth cameras with similar capabilities to this RealSense D400, it's easy to imagine a concert or event with thousands of combined images and the extremely high level of detail that frequently photographed public spaces will contain. In this example, a multicam inside-out array is used to project a single 360-degree point cloud onto a virtual environment. This is a rough example of what an all-in-one 360 depth camera or multiple individual streams would provide. Notably, this environment can be navigated in 6 degrees of freedom with a virtual camera. You are also able to simultaneously view the point cloud capture from a strange location, allowing you to observe yourself or another part of the environment. Today, this is best shown through a VR headset, though in future workflows there will be various display solutions much more elegant and less restrictive than the cumbersome head-mounted displays we have pre-2020.